The next speaker is Professor Fang from Tianjin University of China. He has successfully accomplished over 130 projects of industrial partners in the past 10 years. If you are interested in high-precision manufacturing, perspective of collaborations between industry and academy, then this invited speaker is for you. Please join me in welcoming Professor Fang.
Thanks, Ms. Chair, for your kind introduction. Good afternoon, ladies and gentlemen. Before I start my presentation, I would like to send my special thanks to organizing committee and Professor Rafi Weidram for the invitation to have today's lecture. It is my honor to talk about a topic so-called towards high-precision manufacturing. Today, I will focus on development and applications. Hello? Can you hear? Can you hear me?
Sorry, yeah.
Can you hear me?
Yeah, we can hear you.
Okay, sorry. Okay. So before I start my presentation, I'll show you a map here. Then you can see a black dot here. Actually, this is the place I come from. And the name is Tianjin. So you can see here is the Tianjin city. Tianjin is a relatively small city, only has a population of 50 million people living here. And here is the, you see the city is really beautiful. You can see another scene here. It's a beautiful city. And the university actually is located in the downtown city. And it was established in 1895. There are totally 27 schools and 74 disciplines. There are around 38,000 students. Among them, there are around 50% of them are PhD students and research students. And here is my laboratory. So this laboratory was established in 2005. And today, I'll talk about atomic and close to atomic scale manufacturing. I will also talk about high precision manufacturing of complex surface. And at last, I will show you some applications developed in our laboratory together with industry partners. You know, in early days, there was a computer. However, the computer used so-called electron tubes as a core element for this kind of instrument. And even though this the computer is working well, however, the function is very simple. This is because there are only about 17,000 vacuum tubes in this computer. And with the development of core elements, and people use transistors to develop computers. So you can see the size of the computer much smaller, and the function is better than before. And today we use IC chips to make computers. The size is much more smaller, and the function is more powerful. If we look at the history of this kind of core elements development, let's say the vacuum tube is the first generation core elements, and transistors are second generation core elements. So we may say IC chips is third generation of core elements. Back to 1970s, there was only 2,300 transistors on a IC chip. And in 1990s, there are around several millions transistors on a IC chip. And today, one IC chip may include several tens billions transistors. And if we look at the functional feature size, back to 2018, it's already 7 nanometers. So you can see the size becomes smaller and smaller. And Also in 2018, if we look at the functional feature size, it's around 3 nanometers in development. And today, 3 nanometers processor is already in production. So the question is, what is the next generation of core elements? Maybe we call it a third generation core elements. So with this question, I ask many professors, experts, specialists from academy and also industry. The answer are always different. However, no matter which chip, which elements will be the core elements in future, the one thing is for sure, manufacturing is developed towards atomic and close to atomic scale manufacturing, so-called ACSM. And if we look at the history of the manufacturing development, actually in 1760s, before that, here is a critical point. Before that, there was a manufacturing. However, manufacturing is a kind of craft works. So this kind of craft works actually is experience-based process. And we call maybe the first phase of manufacturing technology. And in this phase of manufacturing technology, the manufacturing is a kind of art. So I visit a Milano museum, so I can see an instrument, or maybe we call it machine, developed by Da Vinci. So this machine, even though we use today's criteria, it's a very comprehensive machine. However, Da Vinci could develop this machine. Others may not be able to do the same. And after this 1760s, there was a machine developed together with the manufacturing development. So people use machine to make components, parts, devices, and the material removal, or maybe we call the material can be addition or removal, down to from sub-millimeters down to micrometers and even nanometers. We call this a manufacturing tool. And in future, the manufacturing actually is at the atomic scale. And if we look at the nature, you see here, this disruptive change happened in nature. You know, but butterfly, before it become butterfly, actually it's not butterfly. It's a kind of pupa. So this pupa can grow bigger and bigger quantitatively. But one day there is a qualitative change from the pupa to butterfly. So we can see this kind of disruptive change. And similarly, from manufacturing 2 to manufacturing 3, actually, there is a disruptive change. And the fundamentals are totally different between manufacturing 2 and manufacturing 3. And we should emphasize here, manufacturing 1, manufacturing 2, and manufacturing 3, they will exist parallelly. Not manufacturing 2 replace manufacturing 3 replace manufacturing 2, or manufacturing 2 replace manufacturing 1. So they are 3 paradigms of manufacturing development. Back to manufacturing 1, it's a kind of craft-based manufacturing, as we mentioned before. And you can see here, people can make this kind of products with a kind of experience, so-called know-how. And mass and repeatable production was not possible at that time. And manufacturing was based on experience or know-how. After manufacturing 1, so there was a manufacturing 2 developed. In this manufacturing tool, there was 4 times disruptive change, so-called Industrial Revolution 1, 2, 3. This kind of manufacturing actually is machine-based manufacturing, and material removal, migration, and addition skills were reduced from sub-millimeters to micrometers and even nanometers. However, if we look at the fundamental foundation, these 4 states are same. They are based on classic theory. For manufacturing 3, so if we look at the fundamental foundation, it is totally different. And the manufacturing objective and the process focus on items directly. So this is the one characteristics of manufacturing 3. And also surface and interface phenomena dominate the manufacturing process. It's different from the conventional manufacturing or manufacturing tool. Quantum effect determine the behavior of items and molecules. So this is the characteristics of manufacturing 3. And also when the skill and the precision of the manufacturing objective are approaching the atomic and close to atomic scale, fundamental theory of manufacturing technology will be changed disruptively from microscopic statics to basic mechanism of interaction between the elementary particles. So this the fundamental difference between manufacturing 2 and the manufacturing 3. And there may be a new process, novel process to be developed in future for this kind of ACSM manufacturing development. And here you can see, as we mentioned before, so the energy will be focused on the items directly. Then we can remove or add or migrate the items to achieve the functional features we designed. These times, so-called manufacturing 3, I can see is coming. It's coming, and the demands from industry become more and more. However, today we back to the current manufacturing development. So I will talk about the high precision manufacturing, more focus on complex geometry manufacturing. In this kind of technology development, minimum achievable chip thickness is very important. It's critical because it is an indicator to present, to show which kind of accuracy we can achieve. So that's why we conduct investigation on minimum achievable chip thickness. So you can see here, experimentally, we can see the chip. You can see here the chip thickness can be down to 3 nanometers. That means we can use cutting process. You know, cutting is a very reliable, cost-effective process. So if we can use cutting process to achieve nanometric material removal, so it's a kind of a progress in manufacturing development. And also based on this kind of development, so we can generate nanometric surface on brittle materials. So you can see here, conventionally, if we cut brittle materials, there is a fracture on the surface. If we can understand the material remove mechanism, we can achieve the surface without fractures and cracks on the surface. And if we look at the chip, you can see the chip is continuous chip for brittle materials. That means we are cutting material in a kind of ductile mode. And the reason we can achieve this kind of nanometric surface is because the mechanism for material removal in nanometric scale is different from conventional machining. In conventional machining, material is removed by shearing. However, in nanometric cutting, actually the material is removed by extrusion. So with this kind of extrusion mechanism, we can achieve nanometric surface on metals, polymers, and even brittle materials. We further develop a process by using an implantation. The reason we use an implantation is because for brittle material, if we cut this kind of material, there is a crack or fracture on the surface. To eliminate fractures and cracks, so we use this kind of idea to generate the ends into the layer to be removed. Then the property of this layer become different. The machinability become better. Then we can remove it without cracks and fracture on the surface. And you can see here, we use the radial distribution function to analyze the layer, modified layer. Then you can see this RDF figure is actually not single crystal anymore. And if we use TEM to further analyze the layer modified, we can see it's a kind of amorphous. That means the material property is changed from brittle to ductile. Then we can cut, we can machine the brittle materials. Here is a silicon. We can achieve nanometric surface. We can even generate complex geometry surface. So if we can use cutting process to generate complex surface with nanometric surface on brittle materials, so it's also a kind of progress in manufacturing development. We further use this process to generate micro features. You can see here micro features. For terahertz, this kind of terahertz find wide applications in industry. However, the output for terahertz is limited. It's very low. So that's a kind of limitation to use terahertz. We generate this kind of micro features, put in the terahertz light source. Then we can increase the output power by 16%. So this is it's used by industry people to obtain the higher power for the output. Another very important material is carbon steel. So there's a problem using nanometric cutting process to generate complex surface on carbon steel, particularly for mold steel. So we developed so-called multi-degree of freedom ultrasonic assisted machining. Ultrasonic assisted machining is not new process. It's not new. So many researchers has done a lot of work in this area. However, very few successful applications in industry. So we developed this kind of technology and further develop this process. Then we use this process generate optical molds, directly cut mold steel to generate optical surface for industry partners. We also develop special tools because we work with companies quite often. We need to generate complex surface and also generate microstructures. We have to use different type of geometry of cutting tools. In the market, there are only straight cutting edge and arc cutting edge tools available. So we have to develop ourselves in our laboratory. So you can see we develop various types of cutting tools for industry partners. Then they can use these kind of tools for micro feature fabrication or complex surface machining. Sometimes the parts can be machined based on the machine accuracy. If we have a high precision machine, then we can generate very precise paths. However, sometimes we expect the path accuracy even higher. Simply based on the machine, we cannot achieve such high accuracy. What we have done is we calibrate the machine accuracy each axis. Then we do the compensation actively. Then we can achieve the path accuracy even higher than machine accuracy. So this is the way for us to increase the machining accuracy. We also develop a so-called unmachine measurement system. So you can see here, we develop a contact mode and also non-contact mode unmachine system. So after machining, we can measure the paths on machine. Then we feed back the error to the controller to further increase the machining accuracy. You know, STM, scanning tunneling microscope, is so far is the highest accurate instrument. So based on this principle, we develop another unmachine measurement system. So because it's very, very accurate approach for the measurement. So based on this principle, we develop our unmachine system. So you can see here, this is length array measured by using this STM. However, the efficiency of this kind of unmachine system is not high. So based on the demand, the requirements, if requirements for accuracy is really high, then we can use this kind of unmachine system. Otherwise, we can use previous two unmachine system for the compensation. Here is a machine we developed for industry partners, the so-called multifunction machine. So this machine can do a micro EDM, electro discharge machining, milling, cutting, and grinding. So as long as we mount the parts on the work material on the machine, then we can do roughing, finishing on one setup, even slotting, drilling on the same machine. So this is a multi-function machine we developed based on the requirements from industry partners. Based on this kind of process and technology development, we further develop some applications for industry partners. So this is one example you can see here. It is actually is a insect. For human being, our view angle is around 60 degrees, but for insects, they can see all surrounding area. This is because they have this kind of very special eyes, so-called compound eyes. So many research organizations, they try to use this kind of structure to develop sensors for positioning and also for imaging. However, this you see here, this profile is very complex, and each small eye also complex. So they simplify this by using semi-sphere, and each eye they use an arc shape. So after simplification, it looks same or similar, but it doesn't function. So we exactly follow this profile and also the microstructure geometry. Then we develop this sensor. So this sensor you put on the table, it can see all surrounding area and also can position high-speed moving object precisely. So here you can see the MTF. So this indication of the imaging performance. So you can see for 45 degree, actually 45 we shoot times 2, it's 90 degrees, and the optical performance still very high, excellent.
Thank you, Professor Fang. We have to close the...
yeah, a few slides more. Yeah, a few slides more. Yeah, come to the end. And we also use this kind of technology to generate, you see the lens array here for optical field imaging. You know, for optical imaging, so there's no need to focus. So we just get a picture, then we can further get the image at different focal distance. And we also develop so-called virtual reality and augmented reality system by using this kind of high precision complex geometry. Previously, they used 4 elements, so now only 1 element, optical elements, can achieve better optical performance with a very compact size. And we also use this kind of technology to generate an intraocular contact lens and to achieve better visual performance. And here is another example for, you know, drug delivery. So there are around 1,300 microneedle array with a very high aspect ratio and surface finish down to 5 nanometers. So we generate this kind of mode for industry partners to develop, to make drug delivery device. There are many applications. This is for artificial joints, hips and knees. So because of the time constraint, I may not talk in details. So there are many applications here for, actually these applications are projects we work with the industry partners. They already use this kind of process technology or products in their companies. So this very brief summary, you can see there are 3 paradigms in manufacturing development, and ACSM will be the leading trend in future manufacturing development. In our laboratory, we have developed processes for industry partners to generate high precision, complex geometry. That's a very brief presentation. Thank you so much.
Thank you so much, Professor Feng. Very fascinating.
Thank you.
Thank you.